Hello everyone. Good afternoon. My name is Venkat. I'm a senior solutions architect at AWS. I'm based out of Northern Virginia and been with AWS for more than 4 years. Um, so I work with enterprise segment customers, and there's always, right, whether whatever the applications come in, the application management, especially people still work on microservices based architectures because that's how you expose your applications to customers, right? So today we'll talk about EKS, and it'll be a little technical because I'll try to cover some of the important topics of EKS and how it differs from the traditional way of doing things, how you can really use AWS EKS platform. So from the agenda perspective, we'll talk about EKS architectures and how you can access the EKS cluster, and how parts communicate within the cluster. And then finally, we talk about, which is an important topic, of how to scale your application. So before we review the EKS architecture, right, let's take a quick step back and understand how we used to run our application, right? The first approach that you see, right, like you just take an application and run it on your EC2 instance, right? So of course, you have an advantage, right? You own everything. You can control the configuration, installation, and everything. When you look at the second approach, right, so where you run a containerized application, right? So you create a container out of your application and then run the multiple containers on your EC2 instance. So the advantage is, right, containers do not contain operating system images. So this makes it more lightweight and portable with significantly less overhead. So when you have containers, right, you can deploy on EC2 instance, but the big challenge comes is, right, when the container starts growing and it becomes too complex and time consuming to manage these and make it, especially dealing with some of the communication challenges, right? That's where the Kubernetes comes in, because the Kubernetes provides automated way of orchestration of these containers. So it makes it easier to deploy, scale, and manage these applications. So the third approach that you see on the right is where pod instead of container running on a worker node. Right, we go more detail into worker node later. So basically, pods are a fundamental building block of Kubernetes application. So they provide a way to group related containers together and manage them as a single unit. Now let's look at Kubernetes architecture. So on the left side, we have the control plane running on the control plane node. So the control plane is like brain of the Kubernetes cluster, right? It is responsible for making decisions like, okay, what is the state of my cluster? Where do I put the resources? Should I bring up new nodes? Where do I place this particular pod, right? If you see node 1 and node 2, that's where our pods are running. So these are called worker nodes. So by managing the worker nodes and pods, the control plane ensures that the cluster is running smoothly and these applications are able to run reliably. And there are a few components that you can see on the screen. Let's talk about those quickly, right? So controller manager, there's a, if you see on the bottom, I think on the left side bottom, you can see controller manager. So it manages controllers that keeps the cluster in a desired state, right? So controllers are responsible for tasks such as ensuring that the number of pods running, right? Let's say if you want to run 5 pods for a particular task, it makes sure that 5 are running, right? And we have another controller that's called cloud controller. It's basically to establish interaction between your Kubernetes cluster and a cloud provider. This includes tasks such as provisioning new nodes, attaching storage nodes, and managing load balancers. The important one is the scheduler, because if you want to deploy a pod in your node, you need to know how to schedule it, right? So scheduler helps you to place a node on a particular pod on a particular node. So while placing a pod on a particular node, it takes into account of factors such as okay, what are the pod's resource requirements? So CPU, memory, and then goes and checks for the nodes available resources and then places the pod. We have another component called Kube API server. So it's basically REST interface for all your commands that coming from externally or internally. It validates and configures the data for API objects such as pods, services, and replication controllers. On the nodes, we have two important components, like kubelet and kubeproxy. So kubelet is a process that runs on each worker node and is responsible for managing the pods that are running on that node. So if you want to, let's say, start a pod, stop pod, you want to monitor the pod, all these instructions goes through kubelet. Kubeproxy is basically a network proxy that runs on each worker node and is responsible for forwarding traffic to other pods running in the system. So it uses a variety of techniques like IP tables or DNS to identify where to send a particular information, right? So let's look at how EKS changes from here, because whatever we've seen as a traditional Kubernetes architecture, let's look at how EKS looks like. So there are two main parts again on the EKS cluster. Same like control plane we have, but here the control plane is managed by AWS and the data plane is managed by customer you. So that means when you create the EKS cluster, AWS provisions a single tenant control plane for you. That means it's not shared with anyone. And there are many advantages of AWS managed control plane compared to what you do traditionally on-prem installations, or if you are doing it on your own in EC2 instances. If you see this architecture, you will see that API servers are spread across availability zones. So this provides you high availability. And they have network load balancers in front of them and to handle connections back to your customer VPC. So, and you also have HCD set up with auto-scaling groups. So Amazon EKS automatically scales your control plane to ensure that it has enough resources to manage the cluster. You do not need to manually resize the control plane. Keep in mind that to a Kubernetes cluster, if you start adding nodes, data nodes, right, your control plane also has to scale such that it can handle all the different traffic coming from the pods in those nodes. And right now we have a limit. You can run up to 13,500 nodes in one EKS cluster. And let's look at different infrastructure options for running these pods. So you can schedule pods on EC2 instances or AWS Fargate. So AWS Fargate is a fully managed container environment. When it comes to managing EC2 instances, again, we have multiple options. So first one is we can refer to this as a self-managed node groups. So in this case, a customer is responsible for managing the operating system, patching it, and making sure it is secure, right? In the second option, which is called managed node group, Amazon manages the instance for you. In that case, so we run the EKS optimized AMI, and we take care of the patching, we take care of draining or rolling out of, basically the complete lifecycle management of the nodes is handled by Amazon in this case. So depending on the scenarios or the expertise, right? Like customers either go for self-managed or the managed node group options. And when talking about EC2 instances, you have multiple options to choose from. You could run on GPU instances, especially with the AI workloads that are being run. There is a high demand for GPU instances. And you can also choose Nitro-based instances, Graviton-based instances. And again, to save some cost, you can also mix with the Spot instances. So now we talked about Kubernetes cluster, right? So, but how do we access it, right? So endpoint access is the way that you connect to your Amazon EKS cluster and manage your applications. So there are a few different options for the endpoint access. Let's look at each one by one. So first, let's talk about the communication between a control plane and a data plane. If you notice on the screen, there is something called EKS hosted ENI. This is a very important concept here, right? So when you create a cluster, we ask you to specify 2 subnets as part of the cluster creation. Why? Because during the cluster creation process, we provision 2 ENIs. ENI means Elastic Network Interface in each subnet. And we use those ENIs to communicate with your data plane. So as you understand, control plane owned by AWS, data plane owned by you, and we need some way to communicate. So the communication happens through these ENI. So when you run a kubectl command from your laptop, right, it goes through EKS public endpoint, which is fronted by network load balancer. And the network load balancer then distributes the traffic to the control plane API servers. So every action decision is taken, like the request is handled by API server. So the control plane API server uses EKS managed ENI to connect to the worker nodes to execute the command. So similar way, worker nodes in the customer VPC can connect to the EKS control plane using either the public endpoint, directly it can go via internet, or it can be using the EKS hosted ENI to the cluster subnet. So how the communication happens is determined by the endpoint setting we have configured in the cluster. If you look here, this is the basically public endpoint. This is the default option. So this means that the requests from worker nodes to the control planes go outside of your VPC, but they stay within Amazon's network. So in order for the worker nodes to connect to the control plane, they need a public IP address and route to an internet gateway or an ad gateway. And the next option is public and private. The next option is both the public and private endpoints are enabled. Kubernetes API request from within the VPC now communicate to the control plane via EKS managed ENI. So it doesn't go out of customer's VPC. So it directly communicates using ENI. And your cluster API server is still accessible from internet because you still have the public endpoint enabled for it. So let's look at the third option, which is a completely private. So in this case, all the traffic to your cluster API server must come from within your cluster VPC or a connected network. There is no public access to your API server from the internet, and any kubectl commands must come from within the VPC or connected network. So the connected network, when we say, it could be you are using a VPN, AWS VPN, or AWS Direct Connect. So these type of deployments are mostly used in government segments where we need a more military, like a DMZ kind of environments where we cannot expose any of these APIs. So let's talk about some networking in EKS, right? So EKS implements the cluster networking through VPC CNI plugin. That's called VPC Container Network Interface plugin. So what CNI allows is Kubernetes pods to allocate an IP address from the VPC network. So that means every pod gets an IP address. So that's a major advantage. That way they can communicate. More specifically, all containers inside the pod share a network namespace and they can communicate with each other using local ports. Let's look at how IP address allocation happens for each pod. When an instance is created, EC2 creates and attaches a primary ENI associated with the primary subnet. So basically, if you bring up EC2 instance, you have an IP address associated. That's a public IP address or private IP addresses. That's attached to your primary ENI. So VPC CNI, what it does is it will automatically allocate a pool of slots from the node subnet to the primary ENI. That's what you see on the screen. Like if you see the primary IP 10.0.0.20 primary, and the secondary IP is 101.20.2.123, right? So when a new pod comes and to land in this node, one of the secondary IP gets assigned to that pod. So now let's look at the because we are using the secondary IP addresses. Okay, now we have a node M5 large. How many pods I can schedule on it if I use the same approach of secondary IPs, right? So if you look at M5 large, right, as per the documentation, it can have maximum of 3 network interfaces, and each network interface can have 10 IP addresses. So that means we have 30 IP addresses here. But one IP address is allocated to the node itself. When you launch an EC2 instance, you have an IP address allocated. So the remaining IP addresses are 29. So you can launch 29 pods in this node. But you can say, oh, my M5 instance is big enough, it can handle more load. If it is 29, what should I do? How can I increase the pod density, right? So for that, we have something called a prefix delegation. If you go to the, when you are assigning, instead of assigning the secondary IP, individual IP, here we'll assign a block of IP addresses. If you look at the, like if you assign a /28, that means you are assigning almost 16 IPv4 addresses in this case. So this is basically a benefit in, like, you can increase the IP address utilization, and you can reduce the scaling overhead, and you can also improve the security, right? So 28 IP addresses, so /28 gives you 16 IP addresses. And we have 27 delegations from 3 ENIs. That's about 432 IP addresses available for you to utilize, right? So now from 29, in the earlier scenario, we have grown suddenly to 432 IP addresses available for this node. So, but we have a limit per node, 110 pods is the limit. So that means as on today, you can run 110 pods in one single M5 node. So, and when I told earlier, like we can run 13,500 nodes, so you can calculate per node how many you can do. So that's basically, it runs into thousands of pods. So the previous diagram, if you look at the secondary IP addresses, I shown you, we have 101, 201, some different IP addresses. Here, if you see, the primary IP is 20, ending with 20, and we have delegated prefixes, and we are using the prefix here. That's how we are getting more IP addresses here. So basically, it's like, so now as we are talking about pod density, that means we are bringing in more pods. So I think it's time to discuss about scaling. So auto scaling is basically a critical feature for any Amazon EKS cluster. So by automatically scaling your cluster up or down on demand, you can improve the performance, reduce cost, and increase reliability. So we have multiple options depending on the situation, what type of scaling mechanism you should use, right? So we have a HPA, which is called horizontal pod autoscaler. And then we have vertical pod autoscaler and cluster autoscaler. So let's dive deep into each one of these. So HPA in EKS communicates with a metric server. So basically, it needs some kind of information to make a decision whether I need to scale or not, right? So metric server is one of the add-on part of the Kubernetes that collects resource info metrics. Basically, okay, what is the CPU consumed right now, right? So that information will be used by HPA to make a decision whether it needs to add more pods into the deployment or not. So basically, there is a target and a desired state. So we match the desired state all the time. And what is VPA? VPA is basically, if you are running a pod and suddenly the memory requirements grow or the CPU requirements grow, you vertically scale the instance so to satisfy the conditions, right? So VPA will automatically scale the pod's resources up right? If the metric value falls below a certain threshold, so VPA will automatically scale the pod resources down. So this is for pods, individual pod. So what we were discussing about is scaling the pods using HPA or VPA, right? But what about the cluster nodes? When more pods join the cluster, we need more nodes to schedule them. That's where the cluster autoscaler come in. So cluster autoscaler is basically a tool that automatically adjusts size of your Kubernetes cluster when one of the following conditions occurs. Like let's say if you have pods coming to schedule and it didn't find any space to put it in one of the node. So basically it hits the condition insufficient resources. Then it knows, okay, I need to add a new node to the cluster so I can place this pod. The another condition is it keeps on monitoring the cluster, and then it finds that, okay, there are so many underutilized EC2 instances. Instead of running 6 pods in one instance, 5 pods in another instance, I could run all the 11 pod in one instance, right? And then it makes the decision and brings down drains the pods from one node, moves it to another node, and delete the node from the system. This really gives you the cost benefit because it really helping you to save the money by identifying the underutilized resources. So let's talk about something very important here, right? So Carpenter, this is new to the mix right now, right? This is as on October 31st, Amazon announced this Carpenter as graduated to beta. Carpenter is basically a node lifecycle manager created by AWS. It's open source. And this is going to be, it's in the process being donated to CNCF, Cloud Native Computing Foundation, as part of Kubernetes Autoscaling Special Interest Group. This is actually well received with 4,900 stars on GitHub as of today, and there are more than 200 contributors from the open source community. And this is not only dedicated to AWS. This can also work on Azure Kubernetes platform. So what happens with the Carpenter, right? So Carpenter works by watching for unschedulable pods in the Kubernetes cluster. If a Carpenter detects an unschedulable pod, it will launch a new node and with appropriate resources to schedule the pod. And also, right, because this developed from the scratch, right, there are a lot of mechanisms added to how it works. So it uses a variety of techniques to scale your cluster, right? And it does the predictive scaling, it does the concurrent scaling, and it does the node pooling. So one of the benefit of using Carpenter is that it can search for the, in case of cluster autoscaler, it will go and select from the existing autoscaling groups. That means it has to pick from certain instance. Here, you will say, okay, I need 4 cores, I need 16 GB RAM, right? Then it will go and find across all the different instance types, which can satisfy that criteria and identify top 20 instances that can be selected to run this, launch this pod, and then chooses the cost efficient option for you, right? So it does all the mechanism behind the scenes. So your pod runs on a most efficient system with cost savings in mind. So it's easier compared to the traditional cluster autoscalers. And because you don't really need to manage your application scaling groups, ASGs, and it will really take care of most of these things, especially with the draining of the resources, rescheduling the pods, and managing your cluster resources efficiently. So this brings to end of my presentation. I would like you to point to some of the resources will be really helpful. One of the things is our EKS workshop. This is the best place to start if you are looking for hands-on experience. Also, if you are considering EKS or planning to migrate to EKS, we are happy to have a conversation, and don't hesitate to reach out. We will help with talk to customers most of the times and try to guide them what's the best option, how they can move to from on-prem to AWS, or if they are already in AWS but they really want to do the modernization, move towards containers and move towards Kubernetes, we are happy to help. And thanks everyone again for your time, and especially special thanks to Ron from AngelBeat.